Okay, guys, so congratulations. You stuck with me. You've made it to 12.7. This is the last section. It's not super long, but it is kind of confusing. Z transforms were new to me, at least the way this book goes about it. I've seen some stuff from it, but not all of it. Z transform is a random variable whose only possible values are non-negative integers, so only positive integers. For n equals 0 and 2, we let p of x equal n, which would give us a sub n, or whatever. So we must define that z is always less than or equal to 1, but it's also not negative. So that's why we put it in absolute value sign. So it is still a probability, but it can have negative values. So I think just to touch there, we can't have negative probability, but we can have a negative value for a discrete variable. So like if I plug -1 into something and I get out a positive value, that's all right. So we're allowed to put negative values in. But for Z transform, this is for a discrete random variable that literally could not have negative integers. So I don't know, this could be something probably with like real life. You need tangible things. So we define the Z transform of X. You're going to see this funky thing used a lot. not even going to try and say it. P of X to the T of Z. So it's basically just the summation of all of these probabilities times our Z transform variable. So it says this is what the book said. It said this is why they're useful, because we actually can create, or we can find the mean from Z transforms, and we can also derive it to find the variance. So this is how they're related. I know it looks like a lot of crazy variables, but when we actually have real numbers to put in, it will look a lot better. So, if you look below, this is, we derive the first mean and the variance, but now we can derive the second moment. So moments, again, kind of a weird thing. It's not really that important to any of these sections, so for the time being, just think of it as the second moment. So if we start with our mean function that we were given with this crazy derivative, we can derive the second moment from the mean. So the mean is like the first moment. The second moment looks like this. And so the only thing that's changed is now I'm squaring that derivative, or finding the second derivative, and adding it to the first moment. So var x takes both of these, and then we have to subtract the second moment from it. So this is coming from there. So again, an example will clear a lot of the questions up. So this is for a binomial random variable. So suppose we toss a coin n times, and the probability of obtaining heads each time is p. Let q equal 1 minus p. If successive coin tosses are independent events, then the mass function describing the random variable x is the number of equals the number of heads is the well-known binomial variable defined by. So we call it binomial because each time we do something, there's a 50-50, or it's either 0 or 1, right? We either got heads or we didn't, got tails or we didn't. So that's why it's binomial. It's either yes or no, 0 or 1. So we define it by, this is probably familiar with the factorials and stuff from just general stats. The Z transform of the random variable x is going to be given by basically the same exact thing, but now we're multiplying it by our Z transform variable, which again splits off, or if you notice, if I multiply all those out together, this is what I would end up with. And all of that actually just ends up being this lovely little formula we can use. So we're now going to use this z transform to determine our mean and variance of the binomial random variable. So if we remember from above, we have these two moments, and we're going to do this for z equals 1. So if I plug z equals 1 in, well, I would just end up with n times p, if you look at it for the first one, because that would be p plus q is just 1 minus p, which is 0. So I have 1 in there, to the n minus 1, n times p, to the n minus 1, you literally just end up with n times p. And then the same thing happens here, since q would be 1 minus 1 is 0. P times 1 is still p. So easy for z equals 1. And so using the equations above this example, we would say that e of x is np and var x is that whole thing plus np minus np squared. So the var x is coming from, again, this crazy second moment minus the first moment, and then we simplified it up here. So that's why we just end up with n times p times q. So this is now a z transform for a geometric random variable. Geometric, think of that as like stuff with exponents in it. If you remember like what a geometric sequence is, that'll probably help jog your memory. Let the random variable x be defined as the number of coin tosses needed to obtain the first heads. Given that the successive tosses are independent, the probability that each toss is heads is given by p, and the probability that each coin is tails is given by q, 1 minus p. Then x follows a geometric random variable where p equals x equals j equals pq to the j minus 1 for all j, or all positive j. And then our z transform is the summation to infinity of that whole geometric random variable times our z transform variable. So for x is greater than 1, we know that we have a geometric sequence that continues to grow. And so therefore we can kind of put our a in x into this form. So p times z and 1 minus qz. So we find that we would have our first, our z transform. Again, remember we have this from up here. And then the only difference for the second transform is that we have multiplied the top by 2 because it's our second one. And it's gone up a degree because it is geometric. So again, if z is 1, the top here kind of just becomes p over 1 minus q squared. And then that would give me 1 over p. And because, quickly note, remember q is equal to 1 minus p. So this is really, if you multiply that by 1, I have 1 minus p. So that's where the p squared comes in. And then for var, if I put 1 in for z, but also replace q with 1 minus p, I would end up with this as my answer. So I know it doesn't make a lot of sense right now, but we're going to finish this whole thing off with one problem for us to do together. So for a given mean, the Poisson, that's how you pronounce it, random variable, has the mass function p of x equals k. Don't worry about what a Poisson random variable is. It's not that important to the following chapters. Okay, so it's e to the negative mu to the n over n factorial. And this is for all k that are non-negative. So we're going to find the mean and variance of a Poisson random variable. So we have to find the mean first, and of a variable, that would be e of large X equal to little k, p of X equal k. Right, that's our just standard how we find the mean for any random variable. Now, the mean of our variable X, well, I pull this out to the front, and I'll tell you why. And it's going to be the summation of, well, our k in this case, or we would be plugging k into the function we have would be k times mu to the k all over k factorial. So I've literally just replaced the n's with k's, and this is equal to, so I brought the e out front because if you remember, e is just a number, and we can bring constants to the front of any summation to make solving easier. So I'm going to always just put that out front. And I would just be left with this again. Sorry, I'm looking at my notes. So we would end up with mu to the k over k minus 1 factorial. Because if you recall, I can split up k and then k minus 1 factorial so that those k's would cancel out. And then we would be left with mu e to the negative mu, parenthesize that, times the summation of mu to the k minus 1 all over k minus 1 factorial. So I pulled out a mu, right, from up here, because if I put that back up there, it would just be mu to the k. So now that would leave me with, need my pencil. That'll leave me with mu out front times e to the negative mu times e to the mu. Okay, and right, I got that from the standard formula. I put this all into e. That's why I was trying to get it all in that form. So that, right, if I multiply these together, they go away, and I'm just left with mu. Perfect. So now, if I want to find the second moment, e of x squared, I basically just have to use the formula from above that we derived, which would give me e of, I have x times x minus 1 plus x. And then I have, again, recalling our rules, plus e of x. Okay, and remember we found e of x above, and that was mu, so I can actually plug that in now. Sorry if you can hear my dog in the background. So plus mu, right? So then e of x squared minus some lambda, which is just a value, we would get e times, or that would literally just be of x times x minus 1. And that would give me that summation of k times k minus 1 times p of k. Okay. So this, I'm going to take this now, and we actually need to solve what we just created. Okay, so again, I have e to the negative mu out front right away, and I have the summation that I had before. Mu to the k all over k factorial. All right, so now I have e to the negative mu of this summation. I'm left with u to the k, because k factorial is k times k minus 1 factorial. And, or I would get rid of it in the top. Sorry, this is not written right. Mu to the k all over k minus 2 factorial, right? Because I changed this into k times k minus 1 by itself to get rid of that in the top to k minus 2 factorial. So we can do that just to get rid of variables. It makes our life easier. So now I can pull out, if I'm plugging in values for k, I would have e to the negative mu times mu squared, summation of mu to the k minus 2 all over k minus 2 factorial. Okay, again, I would get e, or I'd have mu by itself, or sorry, mu squared. I have mu squared here, and then e to the negative mu, e to the mu. I changed it in again, and that just leaves me left with mu squared. So that would make sense. First moment was mu, and the second moment was mu squared. So now all we have to do is find the variance. Oh, and again, we aren't done because e of x squared is actually the second moment plus the first moment. Okay, I'm actually going to make all of this smaller so we have more room for the rest of it. So now I'm going to find the variance, which is our last thing to find for x. So all that is, or one of the formulas we had in the previous, was the second moment, or the second mean times the second moment, or subtracting the second moment of x. And so if we recall from above, we have mu squared plus mu minus mu squared, which gives me mu as our final answer. Okay, so basically it's just a lot of deriving and rearranging the formulas. Poisson variables are pretty difficult, so don't be discouraged if this is confusing. There are more examples in the book that I did not put in the notes, and there are also review problems at the very end of this chapter for every section that I would suggest taking a look at. All the problems that we did throughout this will basically be the same as most of the review problems. So thank you so much, guys, for watching and sticking with me through till the end. All of these concepts from every section is going to aid you in the next few sections when you make models and you are trying to build on the already goal programming, integer programming, decision-making skills we have. So thank you guys so much, and have a great day.